Okay, so as I was standing in line to buy my coffee this morning, I got a call from a Newsweek reporter who, this has been all over the news. So Governor Schwarzenegger vetoed Assembly Bill 1176. There are a lot of news stories about this. Here's one from the Huffington Post. So everybody knows what an acrostic is. You sort of write things out, take the first letter or the nth letter or something like that. You might have done the New York Times acrostic puzzle on some Saturday or Sunday morning. So if you read starting the first letter of each line, there's a message there. And the question was, what are the odds of this happening? So Newsweek wants to know, is this coincidence, or is it engineered? So let's ask, how would you figure out the odds of this happening? How do you make sense of that question? Okay, we all see the message, yes? I don't have to pronounce it. All right, yeah, okay. Okay, so we could focus attention on these 7 lines. Maybe this is part of the message, I'm not sure, but let's focus attention on these 7 lines. Okay, now if we condition on there being 7 lines, so the message isn't of random length, it's a 7-line message, then we can start to ask, what's the chance that the first line would start with an F, and the second line would start with a U, and the third line would start with a C, et cetera, right? But what is a model, what is a reasonable chance model for how these lines get started with various letters? So one model is the monkeys banging on typewriters model, that every letter key on the typewriter is equally likely to be hit every time a line is started, and that the lines start independently, so forth and so on. So there would be a 1 out of 26 chance that this line would start with an F, and a 1 out of 26 chance that this line would start with a U, and a 1 out of 26 chance this line would start with a C, et cetera. Right? That's a model. Okay. Do you think that's a reasonable model? No. Okay, why would that not be a particularly reasonable model for how letters are starting lines? Okay, so it has to be part of a word, it has to make sense with what came before and what came after. Let's start with the crudest things. This consists entirely of English words, right, aside from 1176. Yep. In English, not every letter of the alphabet occurs equally often, right? Some letters are much more frequent than others. That's why they're where they are on the typewriter, to make it easy to type. That's why the Morse code symbols for A and S are shorter shorter than an E, or shorter than many of the other symbols, right? Because they're used more often, it saves time. Okay, so in fact, letters don't have equal frequency in English. And you could say, and moreover, the frequency with which letters occur as the first letter of a word is different from the frequency with which letters occur in words as a whole. Okay, so initial letter, K is a rather uncommon letter to start a word with, compared with, say, S. Okay? So a different model to compare this to, rather than monkeys banging on typewriters constrained to type 7 lines but not constrained to write English words, would be, suppose that you started each of these lines with an English word pulled at random from all of English. Okay? Then the probability that this line would start with an F would be the relative frequency of words that start with F in the English language. Okay? People have tabulated stuff like that. In fact, there's a Wikipedia article that claims to go to the Gutenberg corpus and work it out. And I just transcribed some of these things. So it turns out that F occurs as the initial letter of words in that corpus a little under 4% of the time. C about the same. K only about 0.7% of the time. O about 6% of the time. U about 1% of the time. And Y a little over 1.5% of the time. Okay? So a different model might be that you start each line with a word pulled at random from the English language. Again, that's not constrained to sort of make sense with what comes before with what comes after, but it's a model. Okay, so the first thing saying letters are equally likely to be pulled, if you then the probability that you would get those seven letters in that order would be 1/26 to the 7th, which is 1 in 8 billion, roughly. Okay. Now the second model, which says let's honor the relative frequency with which various letters start words in English, that gives us actually an even more astronomically surprising chance. It turns out to be 1 in about 487 billion that you would get 7 words starting with those letters in that order if you were pulling words at random out of the English language. Everybody with me so far? Okay. But there's another thing you could do, which is perhaps the kindest and gentlest thing you could do to Arnold under the circumstances, which is to say, let's suppose that we simply knew that the initial words were going to be for, unnecessary, care, kicks, yet, overwhelmingly, and unnecessary. We've got unnecessary twice there, don't we? And ask, how many ways could those 7 words be arranged as the first words of lines? Okay? And this is very much like a homework problem that you guys have already done, or a problem in the chapter, right? You've got 7 letters with 1 duplicate, U occurs twice, and you ask, sort of, how many distinguishable ways are there of arranging those 7 letters, including the duplicate? So, sorry? So it's 7 factorial, but for the fact that the U occurs twice. So you end up dividing by 2. But another way to think about it is, from the 7 places, you need to pick 2 to put the U's. So that's 7 choose 2, which is 7 times 6 divided by 2. 7 times 6 is 42, divided by 2 is 21, right? Then having put the 2 U's down, you now have 5 places to put the F, 4 to put the C, 3 to put the K, 2 to put the Y, and then the O goes wherever's left, right? So you get 7 times 6 over 2, times 5, times 4, times 3, times 2. So that's 2,520. Sorry? It wouldn't make sense to rearrange it, but in some sense it's sort of like, let's back away from what we're claiming happened at random and kind of put the okay. So at any rate, so if you want to compare the numbers, if you pretended that somebody was banging on a typewriter in such a way that every letter is equally likely, you get about 1 in 8 billion. If they bang away on a typewriter, but in such a way that they're typing English, so they're sort of generating real English words selected at random from a very big corpus, people actually using English with the frequencies at which words occur, then you would get a number like 1 in 486 billion. And even if you simply say they randomize the order of the lines, it's 1 in about 2,500. What's another model? There's one more kind of obvious model to compare this to. What else might be done at random? Sorry? Will you end the line? Okay. So we chose to look at the initial letters. And might have looked at the end letters, and there may be more than one way to hide a pattern. But let's start with the letter itself, with this particular document. and say, what if we took the words that occurred in this document and put them in a random order, right? We're sort of picking 7 of the words in this document in some order, and they happen to spell out some particular thing, right? So we could imagine taking 7 words at random from the whole document in some particular order and asking what the chance is that they spelled this particular message. So the last thing we did was we're just jumbling these 7 lines as opposed to taking 7 words. We could take the 7 words as well. I didn't do that calculation, but maybe you guys want to think about it. In fact, maybe I'll assign that as an extra credit assignment or something like that. So I'll post something. Questions about this? Another exciting day in the life of a statistician. Yeah. Oh, the Huffington Post article? And this is one of many, many, many news articles that refer to this. My goodness, what a coincidence, said Schwarzenegger's spokesperson, Aaron McClear. I suppose when you do so many vetoes, something like this is bound to happen.
I mean, he has people proofing his messages, right? So if it wasn't meant to be some, I'm an editor, you catch that.
Sorry?
So if you're like proofreading message, like letters, you don't need that.
Yeah, I don't know whether you look for it or whether you adjust the line breaks to make sure the message is there or what. I don't know how. Yeah. Anyway, just a little bit of entertainment. Okay. I'm going to quit this. Okay. We were talking last time about the binomial distribution, and I'm going to turn this. What do I want to do to this in order to change source? That's good. All right, and let me raise the board. We'll do some board work for a little bit. Okay, we were talking about the binomial distribution last time, and that's basically the distribution of the number of tickets labeled 1 you get if you draw at random with replacement independently from a box of numbered tickets where you have some number of tickets labeled 0 and some number labeled 1. So if you have in all capital N tickets and the number of tickets labeled 0 is n times 1 minus p, and the number labeled 1 is n times p. Whoops, I don't need that paren, do I? And I'm going to draw independently and I'm going to let x be the number of tickets So x is the number of tickets labeled 1 I get in this sample of size little n drawn from a population of size big N, where I draw at random with replacement independently. Okay, so if I do that, then x has a binomial distribution with parameters n and p. And in particular, I can write down the probability that x is equal to each of its possible values. What are the possible values of x? 0, 1, et cetera, on up to little n. Those are the possible values I can get. And what I have is that the probability that big X is equal to some value little x is equal to what? Okay, little n, choose x. Okay, what are these terms coming from? Well, to get little x tickets labeled 1, I have to draw a ticket labeled 1 x times. In each draw, the chance I get a ticket labeled 1 is little p. the draws are independent, so that the chance that that happens x times is p to the x. I also have to get the remaining n minus x tickets have to be tickets labeled 0. The chance I get a ticket labeled 0 in each draw is 1 minus p. That has to happen n minus x times. Those draws are independent, so the chance that that happens is 1 minus p to the n minus x. Both of those things have to happen together, and they're independent, so I'm multiplying that. And then there's this many different ways it can happen, because those little x tickets labeled 1 could be the first x, they could be the last x, it could be the first, and then the last x minus 1, et cetera, et cetera. There's this many different orderings of draws that result, this many different ways of ordering n draws so that x of them have 1s and n minus x of them have 0s. Now, we can think of drawing from this box, we can think of getting a ticket labeled 1 as success and getting a ticket labeled 0 as failure. We can think of these as trials. We can think of counting the number of tickets labeled 1 is the same as adding the numbers on the tickets that you get. Because if you count the number of tickets labeled 1, that's exactly equal to the sum of the numbers on the tickets that you see. Because if you sum, when you add the 1s together, that counts the 1s. When you add the 0s together, it doesn't contribute anything to the sum. So the number of tickets labeled 1 is the same as the sum of the values on the tickets that you see. So far, so good? OK. So the key ingredient is there's some proportion of tickets labeled 1. We have a 0, 1 box. We're drawing a fixed number of times. The draws are independent. And what we're doing is counting how many times we get a ticket labeled 1, or adding the values on the tickets we see. Same difference, same thing. OK, now we're going to think about, and so I could write the probability distribution this way, and this is true for x equals 0, 1, 2, on up to n. Right? Those are the values for which this makes sense. For any other value of x, the probability is 0. Right? Can't get 17 tickets labeled 1 and 5 draws. So far, so good? I could also write this as a table. I could write x and the probability that x equals little x, and what would go under 0. It's not a trick. What's the chance I get no tickets labeled 1 in little n draws from a box of tickets of which a fraction p are labeled 1 and a fraction 1 minus p are labeled 0? Yep, and n choose 0 is 1, OK? And p to the 0, which is 1. And 1 minus p to the n minus 0, which is 1 minus p to the n, right? OK, so this would be 1 minus p to the n. And we could fill out a table terminating in n, which would have us p to the n would be the probability that we get all the tickets we get are labeled 1. OK, so we could represent the probability distribution as a formula or as a table. So far, so good? OK. All right. Let's think about doing a different experiment using the same box of tickets. So this experiment was draw repeatedly at random with replacement, count how many tickets labeled 1 you get. Right, here's a different experiment. OK, so draw a ticket at random with replacement, independent draws until the first time you get a ticket labeled 1. All right, so what's the difference here? With a binomial, we were drawing a fixed number of times little n. Here, we are drawing a random number of times. Okay? With a binomial, we were counting how many tickets we got labeled 1. What are we going to do here? Let's let x equals the number of draws it takes. Okay, so we're going to let here our variable, this is a random variable. This is the thing that we're defining from this experiment. What it's going to be is how many draws does it take until the first time you see a ticket labeled 1? If you draw at random with replacement. Right? So x is going to have some probability distribution. What are the possible values of x? Can you get a ticket labeled 1 without drawing at all? No. You got to draw at least once. Yes? Okay. And what's the chance you get a ticket labeled 1 on the first draw? We got a fraction p of these in here, right? There's not one ticket labeled 0 and one labeled 1. There's n times 1 minus p labeled 0 and n times p labeled 1. I reach in, I pull out a ticket. What's the chance I get a ticket labeled 1? Okay, so some people are reasoning it out. So if you're equally likely to pull each ticket out, then the probability that you get a ticket labeled 1 would be the fraction of tickets in the box that are labeled 1. Yes? Okay, and if it's not obvious that that fraction is p, let's just work it out. How many tickets in the box are labeled 1? You have n times p. How many tickets are there in the box in all? N. Right? Okay, so the chance that you get a ticket labeled 1 on the first draw is p. If that happens, game over, big X is equal to 1. Okay? What's the chance that X is equal to 2? How does it happen that you get the first ticket labeled 1 on the second draw? Okay, so for this to happen, you have to not get a ticket labeled 1 on the first draw. Right? You have to get a ticket labeled 0 on the first draw. Because if you got a ticket labeled 1 on the first draw, game over. Right? So you have to get a ticket labeled 0 on the first draw, and then get a ticket labeled 1 on the second draw. Right? What's the chance you get a ticket labeled 0 on the first draw? Okay. Now the draws are independent, right? Whatever ticket, that ticket labeled 0, you put it back in, you stir everything up again, and now you pull out a ticket again. Okay. What's the chance that that ticket is a 1? P. Okay. The draws are independent, so the probability that I get a ticket labeled 0 and then a ticket labeled 1 is just the product of those probabilities. Okay. What's the chance X is equal to 3? Well, I have to get a ticket labeled 0 on the first draw. Then I have to get a ticket labeled 0 on the second draw. And then I have to get ticket labeled 1 on the third draw. They're all independent. So the chance that that happens is 1 minus p times 1 minus p times p, which looks like 1 minus p squared times p. Okay, what's the probability that x is equal to little x? The general case. For x equal 1, 2, 3. Right? In order to get a ticket labeled 1 for the first time on the xth draw, the first x minus 1 draws have to give me tickets labeled 0, and then the xth draw has to give me a ticket labeled 1. The draws are all independent, so the chance that that happens is the product of the probability that I get a ticket labeled 0 x minus 1 times and the time that the probability that I get a ticket labeled 1 on the xth time. So, okay? Okay. So this distribution is called the geometric distribution. And it has one parameter. What's its parameter? P, right? If you change the proportion of tickets labeled 1 in the box, you change the probability distribution. Yep. The more tickets labeled 1 you have in the box, is it more likely that X is small or that X is big if you have a lot of tickets labeled 1 in the box? Small, big, big, small. Big, medium, small. $1.380. Okay, the more tickets labeled 1 in the box, the greater the proportion of tickets labeled 1 in the box, the more likely it is that you'll get a ticket labeled 1 the first draw, right? It's kind of harder to avoid getting a ticket labeled 1 the larger the fraction of tickets labeled 1 in the box, and so the fewer draws it's likely to take. Okay, in the limit, suppose that all that's in the box are tickets labeled 1. Well, then you're going to get a ticket labeled 1 the first time you draw, right? Is that what this formula tells you? What's the probability that X equals 1 if P is equal to 100%? It's 1, right? It's just this. Probability X equals 1 if P is equal to 100% is 1. It's 100%, right? Okay. And conversely, if all the tickets are labeled 0, you'll keep drawing forever. You'll never get a ticket labeled 1. Yep. Okay, and in between is in between. Okay. So we have the same box of tickets. We did a different experiment. We counted a different thing. We're still counting something. We're counting the number of draws. Before we were counting the number of tickets labeled 1. Okay. The draws are still independent. So a lot of the words are the same as they were for the binomial, but the experiment's different. Same box of tickets, proportion P of tickets labeled 1, draws still independent, but then we're doing something different with the draws. We have the same mapping. Question, yes?
What if, say you're at a casino and you have different ways to win, but there's different probabilities for each different way to win? How would you calculate that using this formula?
The question is how does this interplay with a situation where you have different ways of winning that have different payoff odds or different chance odds and different payoff odds? And unless you can reduce it to a single trial, okay, so this would be related to, like, we play the following game. We roll dice. We roll a pair of dice, and if it comes up doubles, I win. If it comes up anything but doubles, you win. And this would let me look at things like, what's the probability that we have to roll the dice 7 times before I win for the first time? But this is looking at things where we're drawing from one box. We can sort of reduce it to drawing from one box, where getting a ticket labeled 1 is like success. In that case, it would be like getting doubles. And getting anything but the ticket labeled 1 is failure. Getting a ticket labeled 0 is failure. So in that case, anything but doubles. So this is about repeated trials that are independent, same probability of success in every trial. And we're counting the number of trials to the first success. So talking about zeros and ones is the same as talking about successes and failures. Right? And independence of the draws is like independence of the trials that can each result in success or failure. So this would be the things like the distribution of the number of times you have to toss a coin until the first time it lands heads. Number of times you have to roll a pair of dice until the first time you get doubles. All right. Is this kind of holding together? Yes? We're going to work out what the distribution is of the number of draws until the second time you roll doubles or get heads or something like that. In fact, that's the next thing we'll do. Are there questions about this before we move on to that? Okay, so that's another experiment. We can think of the same box of tickets. We can again think about drawing at random with replacement independently from the box. But instead of drawing until the first time we get a ticket labeled 1, we can think about drawing until the rth time we get a ticket labeled 1. And again, we're going to let x be the number of draws it takes for that to happen. So what's the probability that x is equal to x where, okay, so how many, you have to draw at least a certain number of times to get a ticket labeled 1 r times, right? You got to draw at least r times or you can't get r tickets labeled 1. Okay. What's the chance that x is equal to r? What has to happen for you to get a ticket labeled 1 for the rth time on the rth draw, the rth time you reach into the box and pull a ticket out? Every single time you reached in, you had to have gotten a ticket labeled 1, right? What's the chance that that happens the first time you reach in? Chance you get a ticket labeled 1 the first time is p. Chance you get a ticket labeled 1 the second time is p. They're independent, so the chance both of those things happen is p squared. Chance you get a ticket labeled 1 the third time, p. Okay, so this is p to the r. Yep. Okay. Yes.
Don't you have to not get 1, so you get like 0, 0, 0, and then 1 on the rth time?
This is a chance, this is the chance that all r of the first r draws give you tickets labeled 1. Right? It's the chance that every single one of the times you reached in r times, every time you reached in, you got a ticket labeled 1. Okay, so each of those gives you a factor of p. All right, now let's ask, what's the chance that x equals r plus 1? Now it gets interesting. To me, anyway. What this is, okay, what does it mean for x to equal r plus 1? It means that I get a ticket labeled 1 the rth time on the r plus first draw. So in r plus 1 draws, what has to have happened? I must have a 0, and I must have r tickets labeled 1. I have to have 1, 0, r1s, and a little bit more has to happen than that. That's not quite enough. Because if it was the first r tickets that were labeled 1, I would have been done, and x would have been equal to r. So it can't be the first r tickets that are labeled 1. There has to be at least 1, 0 in the first r. And then the r plus first has to be a 1. Okay, so just a little example, right? Let's talk about r equal 2. Let's talk about r equal 3. Okay, and we want to find what's the probability that x is equal to 4. Okay, so what are the outcomes that could work? I could get 0, 1, 1, 1. I could get, 1, 0, 1, 1, 1, 1, 0, 1. But I can't get 1, 1, 1, 0. Because if I got 1, 1, 1, 0, that would be x equals 3, not x equal 4. Right? I would have gotten the third ticket, the ticket labeled 1 for the third time on the third draw, not on the fourth draw. Is this everybody with me? Okay, so
So r is the number of ones.
R is Yeah, I want to get R tickets labeled 1. I'm going to keep drawing until I get R tickets labeled 1, and then I stop. Okay. This is, the logic behind this is very, very, very close to one of the homework problems. So this is helpful, I hope. All right. So what has to happen? So what's the probability that x is equal to r plus 1? Well, I know that the r plus first trial has to give me a ticket labeled 1, because if not, I would have stopped before then, right? The last draw has to be a draw that gives a ticket labeled 1. So far, does this make sense? The r plus first draw must have given me 1. Because if the r plus first draw was a 0, then I could have stopped at r, because I already had r successes, r tickets labeled 1. Okay, so I'm going to have a factor of p for getting a ticket labeled 1 on the r plus first draw. Now, what has to happen in the first r draws? Okay, I've got to get, yeah, so from the first r draws, one of them has to give me a 0, and the other r minus 1 have to give me 1s. All right, so I'm saying that in r trials, r draws from that box of tickets, I need to get r minus 1 tickets labeled 1 and 1 ticket labeled 0. Fixed number of draws, independent draws, same probability of success, doing the draws with replacement, et cetera, et cetera. What's the probability I get r minus 1 successes in r trials? Okay. Yep. It's placeholders rather than variables. Sure. Okay. Let's go back to the r equals 3. All right. So I'm saying that in the first 3 trials, need 2 1s and 1 0, right? So I need to get r minus 1 is 2 successes in the first 3 trials and 1 failure, 1 0 in the first 3 trials. Okay? Fixed number of trials, 3. Same probability p of getting a ticket labeled 1 in each trial. All independent. Does this sound like something we talked about today? Binomial, yes? Okay, so what's the probability that I get 2 successes and 1 failure in 3 draws from that box? 2 tickets labeled 1 and 1 ticket labeled 0 and 3 independent draws from that box, right? I can use the binomial probability formula to figure that out. There are 3 trials. I need to pick 1 of them in which to have a failure, 2 of them in which to have a success, 1 in which to have a 0, 2 in which to have 1s. Okay, so that's 3, choose 2 ways that can happen, which is 3. And then I need to get 2 successes and 1 failure. 2 tickets labeled 1, 1 ticket labeled 0. Right? In the first 3 trials, so this is what's going on in the first 3 trials. And then in the 4th trial, I have to get a ticket labeled 1. I have to have a success. Yes?
Can you look at the place where you put your 0 and can you do it that way?
Sure. Okay, so if we're doing the, let's think about the r equals 3, right? What are our possibilities? We could get 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1. Those are the possibilities.
Those first and last are the same.
Yeah.
Oh, I'm sorry. 0, 1, what I've done here? 1, 1, 1, 0, 1. Thanks. Thank you. Okay. All right. What's the probability that I get this sequence of 0s and 1s? Well, there's a factor of 1 minus p for getting the 0, and then there's a factor of p, and then there's a factor of p, and then there's a factor of p. Okay. What about this one? Well, there's p, 1 minus p, 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 and this one is p, P, 1 minus P, P. These are all equal to 1 minus P times P cubed, right? There's 3 different ways that that can happen. So I get 3 factors of the same thing. What does that 3 correspond to? It corresponds to which of the first 3 places gets the 0. There are 3 ways of picking that. The last one's got to be a 1. If the last one weren't a 1, I would have already had 3 1s, and I would have stopped the previous stage. Okay, so the general formula here is, in order to get the rth ticket labeled 1 on the r plus first draw, the first r minus 1 draws have to produce one. There has to be one place for the 0, right? And the rest get 1s. And then I get a factor of 1 minus p, and then I get a factor of p to the r. So from the first 3 places, I need to pick one that gets the 0. The chance that I get the 0 is 1 minus p. And then I have in all r tickets labeled 1, so I get p to the r.
Why is it R minus 1?
Yeah, is it R?
Oh, I'm sorry, it is r. You're right. Yeah. Thank you. Okay. From the first r trials, I need to get, in the first r trials, there must be a 0. Yes. Thanks. And then there are r plus 1 trials in all. This corresponds to the r trials on which you got the ticket labeled 1. That corresponds to the 1 more trial on which you got a ticket labeled 0. Okay? You could do r choose r minus 1 as well. It's the same number numerically. N choose n minus 1 is the same as n choose 1, which is n. Picking the one place that gets the 0 is equivalent to picking the r minus 1 places they get. Okay. Yes, question?
How does that equation make sure that the 1 is the very end?
Because we're only allowing we're saying which of the first 3 places gets a 0. Right? So which of the first r places gets a 0. And then at the end, we've got an extra factor of p to get the 1. Yes?
So when your p equals, or p of x equals r plus 1, do you have a p at the end after that? Because isn't r choose 1, 1 minus p to the r, just looking at the first 3 places? Then don't you have to account for your last one?
Okay, so what we've got, if you look at what's going on here, this is the part that corresponds to the binomial without that last p. And then the last p is what's getting the exponent up to r. Because otherwise, in r trials, this would be this to the 1, this to the r minus 1. And then we have an extra p.
Okay.
Is that? Okay. So now we have the pleasure of doing the general term. Yes?
I'm wondering why it's all par to all, but no all par to all minus 1. Because I'm thinking that 1 minus b par to 1 and p par to all, so 1 plus all is more than 1. So
I'm sorry, I'm not following the question.
I'm thinking that it should be all choose 1, 1 minus p, all p, all minus 1.
Okay, so what this is, another way to write this is 1 minus p to the 1, p to the r minus 1, p. Does that make sense? So this is what happens in the first r trials. These exponents add up to r. That's r trials. And then the r plus first trial gives us a ticket labeled 1. Okay, so if I multiply p times p to the r minus 1, I just get p to the r. All right, how do we get to the general term here? Well, again, the last trial's got to give me a ticket labeled 1, or I would have stopped sooner, right? Then in the first x minus 1 trials, I needed to have how many tickets labeled 0 and how many labeled 1? This is a general term. It's bigger than r plus 1 in general, right? So in the first x minus 1 trials, I needed to get r minus 1 tickets labeled 1 and x minus 1 minus r minus 1 tickets labeled 0. So in the first r trials, just write it this way here. Sorry, in first x minus 1 trials need r minus 1 ones and x minus 1 minus r minus 1 zeros. Okay, and then in the xth trial, need a 1. Okay, let's suppose we still have r equals 3, and let's suppose that little x is equal to 15. What has to happen for big X to be equal to 15? Well, in the first 14 trials, I have to have gotten 2, that's r minus 1 is 2 tickets labeled 1, and the rest had to have been tickets labeled 0. And then on the 15th trial, I have to have gotten a ticket labeled 1. So in the first 14 trials, I needed to get 2 tickets labeled 1, 12 tickets labeled 0. Yes? And then I need to get a 1 on the 15th trial. This make sense? Okay, so this is x minus 1, choose r minus 1. And then we're going to get a factor of p to the r minus 1. And then we're going to get a factor of 1 minus p to the x minus 1 minus r minus 1. And then we get another factor of p. And we can simplify that. So this is equal to x minus 1, choose r minus 1, times 1 minus p. How does this exponent simplify? Just x minus r. And then we get a factor of p to the r. Okay, and this is valid for x equal r, r plus 1, r plus 2, etc. Yes?
So that's a general equation we use for everything.
This is the general term of the probability distribution of how many draws it takes to get a ticket labeled 1 for the rth time on the little xth draw. So this has a name also. This is called the negative binomial distribution. Okay. Number of trials it takes to get the rth success in independent trials that have the same probability p of success in each trial. Number of draws from a box of tickets labeled 0 and 1 it takes to get a ticket labeled 1 for the rth time if the proportion of tickets labeled 1 in the box is p and the draws are independent with replacement. Okay, so model would be we're playing cards, we shuffle the deck really well, we deal a hand, you look at it, did you get a full house or not? Okay, put the cards back together, shuffle again, deal a hand, did you get a full house or not? How many times do you have to do that until the 7th time you get a full house? What's the probability distribution of that? That would have a negative binomial distribution with p equal to the chance of a full house in one hand, and r equal to, what did I say, 7? Seventh time you do that? So r would be equal to 7. Yeah. There was a question. I'm sorry.
Why is it r minus 1 instead of r for that general?
This here, why is this r minus 1? In the first x minus 1 trials, you need to get r minus 1 ones. You need to pick which of those x minus 1 trials get the ones. And you're going to get r minus 1 in the first x minus 1, and then the last one is fixed. The last one has to be a 1.
That I guess, but it's just that I still don't really get the r minus 1.
Okay, well, maybe it's wrong. So let's try to do it carefully. So here's a sequence. This is x minus 1 trials in all, and then the xth trial has to give me a 1, right? So in order to end up with r ones in all, in these first x minus 1 trials, there have to be r minus 1 ones. So that those r minus 1 and then the last one give me r ones in all. Okay, so here, you know, if I look at how many of these there have to be r minus 1 ones, and the rest have to be zeros. Just, okay? So from the x minus 1 trials before the last one, where we know what happened, you have to get r minus 1 tickets labeled 1, and the rest have to be tickets labeled 0. And then on the xth trial, you have to get a ticket labeled 1, which gives you r tickets labeled 1 in all, which is when you stop. Yeah. Okay. Yes?
Typically when we have a problem like this, are you going to ask like, are you going to give us r or x?
Well, this is a building block. So why are we doing this? Okay, some probability distributions have names because they come up often. Some probability distributions don't have names. What's important here is the reasoning that leads to the formula, not the formula. And this one happens to have a name, but when you get a problem, you need to figure out what's going on. And sometimes you'll be able to go, oh, yeah, that's like drawing tickets from a box of zeros and ones independently until I get a ticket labeled 1 for the 15th time. I already know the answer to that. I don't have to work it out. But generally, you've got to go back to first principles and figure out whether this is something new or something old. Other questions about this? Okay, so we now have in our inventory 3 probability distributions that have to do with drawing from a 0-1 box. The binomial, which is number of tickets labeled 1 in a fixed number of independent draws from the box. We have the geometric, which is number of draws it takes to get a ticket labeled 1 for the first time in independent draws from the box. And we have the negative binomial, which is number of draws it takes to get a ticket labeled 1 for the rth time in independent draws from the box. Now, negative binomial for r equal 1 sure ought to be the geometric, or we've done something wrong, right? Because that's the same problem description, yes? So does this reduce to the geometric if we put in r equal to 1? Okay, what's x minus 1 choose 0 is 1, right? Anything choose 0 is 1. So this term goes away. 1 minus p to the x minus 1, p to the 1, right? That's what we had before for the geometric. You have to get, in x minus 1 trials, sorry, in x trials, the first x minus 1 trials have to give you tickets labeled 0, and then the xth trial needs to give you a ticket labeled 1. Okay? So the geometric is a special case of the negative binomial. it's the case that corresponds to r equal to 1. You're waiting for the first time you get a ticket labeled 1 as opposed to r possibly bigger than first. Okay? Not okay? Good time to ask questions? All right, we're not done with our box yet. Okay, I'm going to now give this a label. I'm going to call that number capital B, and I'm going to call this number capital G. And again, there's still n tickets in all. So B is for bad, G is for good. So we're thinking about these objects in the box as being labeled as good or bad. G of them are good, B of them are bad, there are n of them in all. Okay? And now, so we still have a 0, 1 box. We still have a proportion P of tickets labeled 1. But I'm going to do my draws without replacement now. I'm going to draw a fixed number, little n, times. And I'm going to let x be the number of tickets labeled 1. Okay, so this is very similar to the binomial, but we're drawing without replacement instead of with replacement. Okay? What's the probability that x equals x? Okay, so first of all, let's think about some constraints that we have. Can n be bigger than big N? No, we can't pull more tickets out of the box than are in the box if we're drawing without replacement. With a binomial, you could keep drawing forever because you're replacing things in between. You're drawing with replacement. Okay, so first of all, we know that you can't get a negative number of tickets labeled 1. So you can't draw a negative number of times. So that's got to be less than n, and that's got to be less than n. Right? We can't. This is a constraint on how many times we can pull things out of the box. We're also going to get some constraints on how many tickets labeled 1 we can get. Okay? What's one constraint on the number of tickets labeled 1? Can you get more tickets labeled 1 than draws? No. Okay. So this has to be less than or equal to n. Can you get more tickets out of the box labeled 1 than there were tickets labeled 1 in the box? Okay. So this has got to be less than or equal to the minimum of n and g. Yes? Everybody with me so far? Okay. There's another constraint also. Let's imagine that I have a box that has 2 tickets labeled 1 and 2 tickets labeled 0. And I reach in 3 times. I got to get at least 1 ticket labeled 1, right? Okay. How do we express that as a little piece of math? What's the logic behind that? Yeah.
The number of times you draw minus the number of tickets.
Okay, so we're thinking about the number of times you draw minus the number of tickets labeled 1. Let's think about it in terms of that n minus x, the number of draws minus the number of tickets labeled 1, right? That has to be less than or equal to what? I don't know. I'm just stand up here making it up. Yeah. Sorry? Well, little x is a variable here. So this is the number of tickets labeled 0 that we get. Okay? What constraints do we have on the number of tickets labeled 0? You can't get any more than n of them, right? And you also can't get any more than there are tickets labeled 0 in the box. Does that make sense? Can't pull out more zeros than there are in the box, can't pull out more ones than there are in the box. Okay. Can we turn these two things into a single set of constraints on x? Well, this one, let's work on this. So minus x is less than or equal to min n comma b minus n. Okay, if I multiply through by -1, what's going to happen? Okay, I'm going to get x has to be greater than or equal to something. N minus something. Does this stay a min? Does this become a max? Okay, let's think about this case that we were just...
Max.
Sorry? It's going to be a max, he says. Cut to the chase. All right, what are we saying? We're saying that you've got to get... you've got to pull out... Okay, so first of all, you've got to get at least 0, right? Okay, so one of these terms ought to give us 0. So min of n and something minus n might give us 0. All right? But then what's the other thing? Well, if you take n minus b tickets out of the, of the n, how many can you accommodate by b, by tickets labeled 0? Right? If this number is I'm sorry, I've got this wrong, don't I? Hang on. Now I'm getting myself all confused. How did we conclude that if we reached in here 3 times, we had to get at least one ticket labeled 1?
Because n is greater than b. The number of tickets.
Because n is greater than b. Okay? The number of draws was bigger than the number of tickets labeled 0. Okay? So if the number of draws is bigger than the number of tickets labeled 0, you got to get at least 1, 1. Okay? So far, so good? So what's going on here? This has to be at least as big as the maximum of 0 and n minus b. It's another way to write it. You can't get a negative number of tickets labeled 1, no matter what. And if there's only b tickets in the box labeled 1, and that's less than the number of times you're drawing, then after you've taken all the tickets labeled 0 out of the box, you then have to start taking tickets labeled 1 out of the box. Yes?
Where does the 0 come from?
It's n minus n, basically. Yes?
Could you use algebra to prove that, like x is greater than and equal to max of 0 and n minus b?
Yeah, you're getting basically minus the max of n and b. Something like that. So, no, you're getting minus the min, and then it turns out in the max when you combine it. Yeah. So let's just think through this. This is some number, okay? And when we flip this, so this is some number. Let's call it q for the sake of argument, okay? Then when we multiply through here by the minus sign, what do we have? We have this is greater than or equal to minus q plus n. Yes? Okay. So that's n minus q, right? Which is n minus q. Okay, q is still the minimum of those things. Yes? But if I take n minus the minimum of n and b, that's the same as the maximum of 0 and n minus b.
That's the part I don't get. Like, how do you turn it into?
Well, there's a negative sign in there. Okay, so we're looking at this is n minus the minimum of n b, right? So suppose the minimum is n. Suppose the minimum here is n. Then that's n minus n is 0. Suppose the minimum is b. Then that's n minus b. Yes? Okay.
So the negative of a minimum is always the maximum?
Well, no. I mean, that's the negative of the min of a negative is the maximum. You know, minus min of minus x is equal to the max of x. Right? There. Okay. All right. So what do we have? We've got that this is less than or greater than or equal to the max of 0 and n minus b. So you can't take a negative number of tickets labeled 1 out of the box. You got to take, after you've taken as many tickets labeled 0 out of the box as you possibly can, you have to start taking tickets labeled 1 out of the box, right? So if the number of draws is bigger than the number of tickets labeled 1, what's left over have to be tickets labeled 1. After you've gotten all the tickets labeled 0 among your n, if n is still bigger than that, then what's left over has to be tickets labeled 1. Right? And then you can't take more tickets labeled 1 out of the box than you draw, than draws you make. And moreover, you can't take more tickets labeled 1 out of the box than there were tickets labeled 1 in the box in the first place. Okay? So this is just getting to the constraints. Now, what's the actual probability? Now we know what the possible values of x are. What's the probability that we get that many tickets labeled 1 when we reach in? So if x satisfies these constraints, then what happens? Well, we're doing something that's called taking a simple random sample. That's drawing a random sample without replacement. We're basically doing it in such a way that every subset of size little n of the capital N tickets that there are in the box is equally likely. Okay, so if I numbered these tickets 1 up to capital N, I might get tickets 1, 2, 3, 4, 5 on up to little n. I might get ticket 2, 3, 4, 5, 6, etc. I might get 1, 7, 9, etc. Every subset of little n of them is equally likely. So how many ways are there of drawing things out of the box in all? Drawing little n of the big N tickets. Okay, so there's big N choose little n, different samples I could get when I draw little n tickets without replacement. Okay. And now for my set to include little n tickets labeled 1 and, sorry, little x tickets labeled 1 and little n minus little x tickets labeled 0, what has to happen? Well, from the little n tickets labeled 1 there are in the box, I need to get x. From the, I'm sorry, let's try again. From the G tickets in the box that are labeled 1, I need to get x. And from the B tickets labeled 0 in the box, I need to get n minus x. Okay. So this is the number of subsets of the capital N objects that give me little x tickets labeled 1 and this many tickets labeled 0. And this is the number of subsets there are in all. And the sampling scheme, this drawing at random without replacement, makes each subset equally likely to be the sample. So each of these ways of pulling, each of these samples is equally likely to be it. This many of them give me what I want, x tickets labeled 1, exactly x tickets labeled 1. Okay. So this is the probability provided x is in these bounds. Otherwise, it's 0. Okay. This has a name as well. This is called the hypergeometric distribution. Okay, and what are its parameters? Well, if I need to know how many tickets there are in the box in all and how many of them are labeled 1, right? Alternatively, I could know how many ones are labeled 0 and how many are labeled 1. It's equivalent. I'm going to write this as n minus g. So the parameters will be how many tickets are there in the box? Of those, how many are labeled 1? And then what's the remaining thing I need to know? How many I'm drawing. Okay? And x is counting how many I get. The possible values are these little x's. The range where the probability is not 0 is this range. Yes?
So you can't have just B and still solve it? You can't have B and
You could take the parameters to be b, g, and n, b, g, and little n, or capital N, big G, and little n, or capital N, big B, and little n. But you need to know how many tickets there are in the box in all and how many are labeled 1. You would know that if you knew both capital G and capital B, or capital G and capital N. So they're okay. All right. If the number of tickets you're pulling out of the box is really, really small compared to the number of tickets there are in the box, then it shouldn't make much difference whether you're sampling with replacement or without replacement. Right? So this ought to be very close to the binomial if little n is a whole lot smaller than big N. So if big N is a million tickets in the box, and you're pulling out 5 of them, then the probability you get from this should correspond to the binomial probability. With what substitution? What are the parameters of the binomial are little n and p. What corresponds to P here? G over n. So P is equal to G over n. The fraction of tickets in the box that are labeled 1. Okay. And the probability that you get pretending that you're sampling with replacement is going to be very, very close to the probability you get for sampling without replacement if the sampling fraction, little n over big N, if this is small. Okay? Not a lot of difference between sampling with and without replacement if the sampling fraction is really small. So far, so good? Okay. Wake up laptop. Okay, here is a little calculator applet. Oh, except it doesn't blow up nicely, does it? Not going to redraw well. Shoot. That's better. Okay, this little applet lets you pick among these probability distributions we've just been talking about, so like negative binomial, and it will then prompt you for the parameters of that distribution. So with a negative binomial, what are the things? There's the fraction of tickets labeled 1 in the box. That's the probability of success in each trial. And then there's how many successes are you waiting for? So that's R. So this is R, and that's P for the negative binomial. And you can ask, for example, let's suppose we're talking about how many, the probability distribution of the number of times I have to toss a fair coin until the 10th time I get heads. Okay, so the chance of success in each trial is a half. And I can ask, what's the chance that I have to wait at least that I have to try at least 5 times for that to happen? What's it going to be? Can I get 10 heads in 5 tosses of the coin? No. Okay. So this ought to be 100%. I definitely have to wait at least 5. I have to try at least 5 times. What about 15? Okay, I don't have to try at least 15 times. There's a 91% chance that I'm going to have to try at least 15 times before I get 10 heads. Does this make sense? Okay, so you could select hypergeometric. Now what do we have? Population size is how many tickets are there in the box in all. Good in population is G. Sample size is little n. How many times are you reaching into the box and drawing something out? So let's suppose we have a population of, I don't know, we have like 30 people in here today. And let's suppose that that we're half men, half women, and we take a sample of size 8. What's the chance that there are at least 10 women in the sample of size 8? What should this give me? 0, right? Why it's not giving me exactly 0, I don't know, but okay. What's the chance there are at least 5? 34% that there are at least 5. What's the chance there's exactly 5? How do I do that? It has to be less than or equal to 5 and greater than or equal to 5, right? That's the way to get exactly 5. So far, so good? Okay. We got a couple minutes. I want to briefly get back to the trade secret data because we talked about that once upon a time at the beginning of class. And we now have sort of the tools to look at this stuff. Question? Yep? We're good? Okay. All right, so you might or might not remember there was this lawsuit. A company sued some of its former employees who had gone off and started a competing business, and after a matter of a month or so, were doing millions of dollars a month in business to customers of their former employer. And the claim was, you guys stole our customer list. It's a trade secret. Stop. And the defendant's response was, you guys are so big, you have so many customers, it was inevitable that we were going to have a big overlap with your customer list. If we're going to sell to anybody, it's going to end up being to your customers because you guys have everybody as a customer. And so the question is, well, was it really inevitable? So let's look at that question. So let's just take one of these pieces and say, okay, of all the customers there are who buy this equipment, everybody conceded that there were at least 90,000 businesses. Of them, 3,300 were customers of the former employers. Of those, 132 were customers of the new business. The overlap between the 3,300 and 132 was 93. All right. How can we turn this into a story that lets us use what we just did with these distributions to say something about whether it's inevitable that the overlap would be that large? Right? We could think of customers being a huge box of tickets, 90,000 tickets in the box. All right? Some of those tickets are labeled 1. 3,310 of them are labeled 1. Those are the customers of the previous employer, WBH. Right? Then suppose that the new business had reached in at random and pulled out 132 tickets. What's the chance that their sample of 132 would contain 93 tickets labeled 1? Right? This is one way to sort of ask about the inevitability question. It's not that they should have found their customers at random or did find their customers at random, but it sort of tells you, was it, it speaks to, was it really inevitable that they would overlap by so much? Okay, so we're imagining, so if we're looking at a random sample without replacement from a population, a box that has 90,000 tickets, of which 3,310 are labeled 1, we take a sample of size little n equals 132, and we're interested in the probability that, that in that sample of 132, 93 or more are labeled 1. Does that make sense? Okay, so just to look at what that probability is. Okay. Okay, that's like the chance of winning the California Lotto 13 weeks in a row. Okay, the other numbers get even worse, but you can sort of formalize things this way. So this is related to, there's a question about fish in a pond and tagging them and capturing them that's very closely related to this thing. Okay, the other number, let's just look at one of the others. So they claim to get, there were 469 companies that advertised in some magazines. 152 of them were customers of the previous employer. 27 were customers of them. The overlap was 26. Okay, what's the chance of that happening? It's like we have a box of 469 tickets, of which 152 are labeled 1. You reach in and pull out a sample of size little n equal 27. What's the chance that 26 or more of the tickets in the sample would be labeled 1? And that number turns out to be there. Okay, so that's like the chance of winning the grand prize in Lotto 2 weeks in a row as a calibration point. Yes?
So we're concluding that that's still customers?
Well, we conclude that it isn't inevitable that their customer lists would overlap by so much. And in fact, had they drawn their customers at random from the pools that they said that they went to without any prior knowledge of their previous employer's customers, it would be pretty unlikely for them to end up with this much overlap. So, yeah, I think it's pretty compelling evidence that they used information they had. So, okay, see you guys next time.